Hello EOS110. This is a tutorial about how to calculate temperature from an energy budget. This tutorial goes along with our Earth's Energy Budget lecture. We spoke about in lecture the idea that in a budget we need to think about energy coming in, which is coming from the sun, and make that equal to energy coming out, the Earth's infrared radiation radiating away from the planet. So our sun energy coming in is equal to our earth energy going out. That's not exactly true. We see that the earth is warming up slightly right now, but for the large part, these are very close to each other. Now in lecture, we talked about how to calculate the sun energy in, that it should be equal to the solar constant times the cross-sectional area of the Earth. So that's pi radius of the Earth squared. And we need to adjust that for the reflection of sunlight from the Earth by 1 minus the albedo. This is Earth's radius. Okay, and we said that that should be equal to the Stefan-Boltzmann constant times the temperature of the Earth to the 4th power times the area from which that radiation is being radiated. That's the surface area of a sphere, in this case the Earth. So 4 pi radius of the Earth squared. And before I go on, I want to say a little bit about this part here. This is the Stefan-Boltzmann equation. It says that the energy emitted by an object is related to the Stefan-Boltzmann constant times the temperature of that object to the 4th power. The Stefan-Boltzmann constant is equal to 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the 4th power. And this temperature here is in units of Kelvin, where a Kelvin is equal to a degree Celsius plus 273.15. Okay, so that's where this part comes into on the Earth energy out. The energy leaving the Earth is related to its temperature times this constant to the 4th power. So we can look at this equation here and we can simplify it a little bit, because we can see that pi occurs in both sides and the radius of the Earth squared appears in both sides. So those things cancel. We have a situation, an equation that's the solar constant times 1 minus the albedo equal to Stefan-Boltzmann constant times the temperature here of the Earth is what we're looking at to the 4th power times 4. Okay, that's a little bit easier to deal with. I'm now going to solve for the temperature here. It's the 4th root of the solar constant times 1 minus the albedo all over Stefan-Boltzmann constant times 4. Okay, so in an exam situation, I wouldn't expect you to have to lay all these equations out to derive this equation, but I will expect you to be able to use an equation like this. Now in class, looked at a calculation where the solar constant was one appropriate for the Earth, which is 1366 watts per meter squared. And we used an albedo similar to the actual Earth, which at present is about 0.3. When we did that, for these values, we got a temperature of the Earth equal to 255 Kelvin. And when we convert that to degrees Celsius here, we found that that was equal to minus 18 degrees Celsius. Recall, the reason the temperature is so low here has to do with the fact that we're not including the greenhouse effect of some of our atmospheric gases in this equation here. Now let's do one more example to demonstrate how to use this calculation. A long time ago, it's thought that the Earth might have been covered by snow. Sometimes you hear this called snowball Earth. And that even the oceans were covered with a thick layer of ice. And at that time, we would have expected the albedo to be quite a bit higher. So let's do a calculation with a higher albedo to demonstrate. Let's suppose the albedo is twice what it is present. We'll try an example with an albedo equal to 0.6. Okay, so the temperature of our snowball Earth then, call it SE for snowball, I guess, is going to be equal to that fourth root times my solar constant, which hasn't changed in this case, still 1366, times 1 minus the albedo, but my albedo is now 0.6. Stefan-Boltzmann constant, always a constant, 5.67 times 10 to the minus 8. We'll put our units in here. Our solar constant is watts per meter squared, and our Stefan-Boltzmann constant is watts per meter squared, Kelvin to the fourth. And we've also got that 4 in there to consider. Okay, so if we bring our calculator into play here, 1366 times 1 minus 0.6, that's 0.4. So I'm just going to multiply by 0.4. Divided by 5.67 exponent minus 8, and divided by 4. So this value represents the number inside the fourth root here. Now we can take the fourth root. You can either take it directly on your calculator, or you can take the square root twice, which is what I'll do here. So there's one square root, and a second one. I get 221 Kelvin. Which again we can convert to degrees Celsius by subtracting 273.15 minus 51.6 degrees Celsius. Okay, so in this calculation, although we're neglecting the atmosphere, which is of course important, we can see an indication of how important the albedo is. With a higher albedo and more sunlight being reflected, a substantially colder temperature would be expected. Okay, I hope that helps with using this equation to calculate temperature from an energy budget.